Let's continue with our discussion of the complex conjugate theorem that we looked at in the last video. That basically the point is if a plus bi is a zero of a polynomial, then a minus bi will also be a zero as long as the polynomial has real number coefficients. And we already talked about that first example there. Let's go right on to exercise 5. Show that both 1 plus I and 1 minus I are zeros of this polynomial f of x equals x squared minus 2x plus 2. So we're basically just verifying the theorem here. And I'm going to do this problem in two totally different ways. I think it's worth seeing these two different ways. Now, you would only have to do it one of the two ways. You would never have to do the same problem two different ways. And so the first way, we're going to actually evaluate the polynomial at the numbers we've been given. So I'm actually going to plug in 1 plus I into the function f that we're talking about here. So our function's right here. And if I plug in 1 plus I get 1 plus I in parentheses squared minus 2 times 1 plus I in parentheses plus 2. And if 1 plus I is a 0, this should be equal to 0. So let's go ahead and see what it turns out to be. I have to multiply 1 plus I times itself. And I'm just going to recopy everything else here. So when I multiply out 1 plus I times 1 plus I get 1 plus 1I plus 1I is plus 2I plus I squared. Then I have to distribute the negative 2 through the next parentheses here. So I get minus 2 minus 2I plus 2. And so I have 1 plus 2I plus I squared is negative 1. Minus 2 minus 2I plus 2. And now just notice I got 2I minus 2I. I got 1 minus 1. 2 minus 2, sure enough, this all adds up to 0. And that's exactly, so 1 plus I is a 0 of the polynomial f of x here. Now we also have to check the other value, 1 minus I. Now the theorem says that if we get 1, the other one's got to work. So we know this has to work, but let's just verify here. And it's almost the same calculation, just a little bit different because I have 1 minus I squared minus 2 times 1 minus I plus 2. And again, I got to multiply out the first square. And I get 1 times 1 is 1. Now I get minus I plus a minus I is minus 2I. But a negative I times a negative I is plus I squared. Distribute the negative 2 gives me negative 2 plus 2I plus 2. So this looks like 1 minus 2I plus, now the I squared, the positive I squared is negative 1. That's the meaning of I. And so signs are in slightly different positions, but I got minus 2I plus 2I. I got 1 minus 1 again, minus 2 plus 2. So we get 0. So 1 minus I is also a 0 of f of x. So that's one way to verify that those two complex numbers are both zeros of the given polynomial. But now I'm going to do this a totally different way. And if you like this way better, of course you can use it. we're actually going to solve f of x equals 0. We're going to set the function expression equal to 0 and solve. So I'm going to say I'm going to solve x squared minus 2x plus 2. So I'm taking that function expression and I'm setting it equal to 0 and I'm solving for x. So I'm actually kind of working backwards. I'm finding the x values that will make the function equal to 0. Now this is a quadratic equation that I can try to factor, and yet now signs would both have to be minus if this is going to work, but I don't. You can play around with it for a minute. It's not factorable. So to solve, we have to use the quadratic formula. Where a is 1, b is negative 2, c is 2. So we got to plug into a quadratic formula here, and we get x is equal to negative a negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 2, all over 2 times 1. And what does that simplify to? Let's see. X is equal to 2 plus or minus the square root of 4 minus 8 over 2. And I'm going to bring that up over here on the side. So I have x is equal to 2 plus or minus the square root of negative 4 over 2. And here's where we have a negative number inside a square root sign, so there's no real solution here. But there are complex number solutions, so I can rewrite that square root. In fact, I'm going to rewrite the whole thing here. 2 plus or minus, that's going to be I times the square root of 4 over 2, or 2 plus or minus, the square root of 4 is 2, so I can just say that's 2 times I over 2. And now I can cancel 2's, but to do that I need to factor out a 2 from the entire numerator, right? So that's, I have to factor out a 2 from both terms up above. 2 times 1 plus or minus I over 2. And the 2's cancel, so I get x is equal to 1 plus or minus I. And there's our 1 plus I and 1 minus I. X equals 1 plus I. And we get x equals 1 minus I are the solutions. And so they are zeros of the polynomial because they're the values of x that make f of x equal to 0. So a totally different way of verifying the fact that these are both zeros. So they are both zeros of f of x. Okay, now we're done with the problem, but there's a little bit more, just a little bit more I want to say about this. So we are done, but I want to make an observation before we quit this about this function f of x equals x squared minus 2x plus 2 with complex zeros, 1 plus I, 1 minus I. So there are two complex zeros. But if we were to graph this function, now this is an easy graph for you guys because this is a quadratic function. We know the graph is a parabola, and it doesn't take long to work through the steps with this one. And I'm not going to write out the work, but the x-coordinate of the vertex is 1. It's easy to verify. And when we plug in 1 here, I think we get y-coordinate 1. So the vertex is actually at the point 1, 1. And The y-intercept is 2. And we know the shape because the lead coefficient is positive, right? So there's that y-intercept at 2. And just notice that there are no x-intercepts for that graph because the graph lies totally above the x-axis. There are no x-intercepts, and so there are no real zeros, but there are 2 complex zeros because a second degree polynomial will always have 2 complex zeros. That's the fundamental theorem of algebra. Okay, that's all I wanted to observe. We're going to go on to some more exercises in the next video.